Hey guys, welcome back. So, this is going to be part one of a several part series going over electrical for my race car. Now, you're going to see some things that are going to make sense and they're kind of commonplace when you're building a race car. Some of this is going to be stuff you've never seen before. So, this diagram kind of sums up what we're thinking. And let me say this real quick before we go over this. This is like the fifth or sixth video I've filmed, and I decided not to upload any of the others because I just kept changing my mind as I researched what I should do. So this is after a lot of work. I've put probably 50, 60 hours researching how to build this. And this is kind of what I think we're going to do. So, in simple terms, what you see here is what we're going to do. So there's going to be no alternator on the car. We're going to put a big lithium battery. There's a kill switch in the rear bumper, so you can kill the car. Like if you have a wreck or something, they can come out there and kill the car. Power comes out of the kill switch. Go through some fuses or switches or relays or whatever. Anyway, there's going to be two main things. There's going to be a 17 volt step-up converter. So this takes whatever the battery voltage is. This is a 12 volt battery, steps it up to 17 volts. And this is going to supply the ignition coils, so we get real hot spark, injectors, the ECU, and the fuel pump. And on the fuel pump, I need the high voltage for performance as well. Now, you'd think the rest of it could run on battery voltage, but we're not going to do that. So we're also going to purchase a 13.8 volt step-up, step-down converter. So this accepts battery voltage and outputs a constant 13.8 volts no matter what. That's going to run our water pump. We're going electric water pump, by the way. Cooling fan, wideband, trans brake, and running lights. That's it. Those 9 things are the only thing, as far as I know, that's going on this car. So, in simple terms, let's start with the very beginning, the battery. So, if you're not going to have an alternator, how big of a battery do you need? So that's a good question. Now, I have been looking at batteries so much it's insane trying to figure out what to do. And I've kind of come to like a universal truth, which is I can't find a battery that I can purchase that I'm really happy with that I think is actually suited for my application. Let me explain what I mean. So when you go on the internet, you start looking at batteries, you can purchase lithium batteries for race cars. There's like 100 options probably. I haven't found any that I think are really good, appropriate, or at all a good value. Let me give you some examples. I found this one battery that was marketed as a 12 volt, 800 cranking amp battery, lithium, weighed like 23 pounds, and it had 100 amp hours or 105 amp hours. So think about that. 12 volt lithium, 105 amp hours, 800 cranking amps. How could you possibly go wrong? Only downside, it was $800. But I just decided after a lot of thought, I was like, you know what, let's pay the money and just buy something that works. Well, there's a problem. That battery so lithium batteries have this thing called a BMS. It's a battery management system. It basically controls the battery. It keeps you from like overcharging it, over discharging it, tearing it up. Maybe I should go over some of that later. But basically, the BMS is critical. And it only had 150 amp BMS in it. And the cells, so the BMS is obviously not rated for 800 amps. Now, the cells that were in the battery are also not rated for 800 amps. So when they claim that you can pull 800 amps, like, well, yeah, technically you can, but, like over here at my wall outlet, I could, stick a piece of copper in there and pull probably 100 amps very briefly before something breaks or melts or catches on fire or trips a breaker. But that's not obviously how it's designed to operate. So we're kind of running into that with these batteries, these off-the-shelf race car lithium batteries. So that's not surprising. I know years back I used to be on a race team, and we used lithium batteries on that car, and we had the same kind of problems. Like they would just die easily, quickly. They had short lives. They worked good while they were working, but they did not last very long. And what I did was I got on YouTube and I started Googling all these I started looking at batteries, and I would find YouTube videos where people actually take these things apart and see how they're built, kind of look at the build quality, the parts that are spec'd, the wire gauges, just really go over like a system overview of how they're built and see if the battery is, high quality and if it's going to last, if it's built well, that kind of stuff. Most of the ones I saw are not that good. And I really didn't see one that I thought was appropriate for my application. Some of them, like if you just kept buying them and paying enough money and hooking enough of them together, like eventually you could basically build a system where you hook enough batteries together that the sum total of all of them would work. But very expensive, and still some stuff's questionable. So in classic fashion, we're just going to roll our own. Now, let's talk a little bit about what that's going to look like. So get used to this. We're not done yet. You can see all these tabs at the bottom. I'm only going to click on the battery one for now. But we're working up a battery plan. And like I said, I've looked at 100 options at this point. So here's what I'm thinking about doing. So you can see here we got specs at the top and then a derated specs. So the derated specs are more like what we're going to treat the battery. So all batteries like lose voltage as you drain them. So this battery would have a nominal voltage of 12.8 volts. And we're going to say 260 amp hours, which is, by the way, a shit ton of capacity. It actually works out to be about 3.3 kilowatt hours. So when you hear of a Tesla, like a P105D, that has a 105 amp hour battery. Well, this has a 3.3 kilowatt. This is a really big battery. Now, what we're going to call this 0% state of charge when it gets down to 12.4 volts. So lithium chemistry is a little different than lead acid. Lead acid, you can drain them at 12.4, that would be considered almost full. But on a lithium, not the case. These things, this particular chemistry that I'm running, which I don't think I mentioned, is called lithium iron phosphate. So it's not lithium ion, it's lithium iron phosphate. And that's important because lithium iron phosphate is a lot safer than lithium ion. And that's a big part of why we're using it, because it's actually more expensive and heavier than lithium ion. So from that perspective, it's like, ugh, gross. But it's safer. And this is my first battery, and it's critical that this stuff works and it's reliable, and I don't want to have a fire. So we're running lithium iron phosphate. So we can see here, when it's dead, it's going to go down to about 12.4 volts. Now this battery has a rated discharge current. So it's rated to do this all day long. You can pull 280 amps. And the reason is because this is actually a 280 amp hour capacity battery. Well, we're going to build it. It's made out of cells. But the cells themselves are rated at 280 amp hours. Now, that's awesome. We can pull 280 all day long. As you can see here, we can actually double that to 560 for 30 seconds. They're rated for this. They'll do more. You can pull on them harder, but it's actually rated for this. Now, granted, if you do this all the time, you're probably going to tear shit up, or at least shorten its life. But you can see here, 280 amps all the time. I mean, we're not going to be doing that pretty much ever. Or, when you start the car, basically. That's about the only time we're ever going to go over that number. So that's the good thing. That's the good news. So what you see here, let's look on this side. This is our bill of materials. Now at the top, I've got some cheaper cells. Down here, these are more expensive. I'll probably just buy these to be safe. So these cells are called Eve. That's the part number, LF280K. These are grade A cells. Now, a quick thing I've learned, I'm just now learning some of this. So grade A cells, when they build batteries, manufacturing companies, like imagine if you were building batteries and every battery you built was perfect. Well, that would mean that you would have to spend all this money on your equipment, your people, your testing, blah, blah, blah. So what they actually do is they set it up to where most of the batteries that come out of the factory are grade A. But some of them don't make the cut. There's a little defect or something's wrong. So they got grade B cells, and there's even ones worse than that where they have other problems. And the downside of running like a grade B cell or whatever is they have shorter life. They can have weird problems, and they're cheaper though. Grade B cells are a lot cheaper, but we're not messing with that. So we're only doing grade A, and we're only buying grade A from somebody that's like trusted to actually sell grade A cells, because another common thing is people pretend they have grade A cells and sell them to you at a great price, and then they're not grade A, they're something terrible. So these are supposed to be legit grade A cells. I believe it's directly from the manufacturer, or not it's a vendor, but anyway, there's the cells. Here's the BMS. This isn't perfect, but it's the best one I found so far. It's made by a company called Dali, and it's a 500 amp BMS. And it actually has Bluetooth. You can connect your phone to it, which is kind of sweet because you can monitor like your battery percentage. Just like your cell phone would tell you, you got 80% battery. I'll be able to hook my phone up and see how much battery my car has. And as you can see, 500 amps continuous, 750 max. So let me show you what that looks like. Okay, this is the BMS I found. So you can pick it up off Amazon, $283. And they're decent. it's not perfect, but I just haven't found a better one. I have no problem spending another couple $100 or at least another, bump it up to 400 if I could get a better one. This one seems okay. I saw the build quality. There are a few issues with these, but like I said, I haven't found a better one. So for now, this is the one we're planning on running. All right, so while we're looking at stuff, check this out. These are the cells I think I'm going to run. This is a different, okay, this isn't the exact link. This is the cheaper ones. I don't have the more expensive ones opened apparently. Let's see if it's that. Nope. All right, so this is the correct cell, but probably not from the right vendor. But it's just this big blue block. These things are kind of big, but check this out. 6,000 cycles. So if you charged this thing and discharged it every single day, in 10 years, that would be 3,600 and whatever cycles. It's going to take forever to wear this battery out. So that's not an issue. The weight is 5.4 kilograms, which is like about 12 pounds. So 4 of these is going to be about 48 pounds, just the cells, which kind of sucks. But that's a trade-off that after lots of thought, I've decided that, you know what, that's okay. I'm going to do that. I'm going to accept the weight. Everything on a race car, pretty much everything in life has pros and cons. And for this system, what we're talking about building, which you see here, where we have the big battery and it powers all this stuff, this thing is going to be heavy. Like we said, that's 48 pounds, just the cells. The BMS is going to weigh like 6 or 7 pounds. There's going to be wires and this thing's going to easily weigh 60 pounds, probably weigh 70 pounds by the time that it's in a case and built up. And oh, that sounds terrible, but it's just reality. That's probably going to be heavy. This thing, we'll get into that in a future video, but this is probably going to weigh 10 pounds. This, I don't really know, but probably 5 pounds. So all of this stuff is going to add weight, but there's benefits to this. And maybe it's obvious, I guess I didn't cover that, but the huge benefit is consistency. Race cars, typically you have to charge the battery after every single pass on a drag car. If you don't run an alternator, even people that run alternators charge their cars every single round because, and I didn't understand why until recently, but even when you have an alternator, it doesn't really keep up on drag cars. You end up with, you have to charge the car every single round. But at least if you have an alternator, it doesn't drain the battery as quickly. So we looked into this, and I'll do another video. I've got another video that'll explain kind of the numbers, like the amp hours and peak amps and average amps and all that stuff. We're going to nerd out on some electrical engineering. But the point of this whole system is for consistency. Because I have this giant battery, this thing is going to run for a long time before it goes dead. And because I have these converters that move the voltage around, this produces a steady, constant voltage. So whether my battery is kicking out 14.5 volts, or 13.5 or 12.5, this is going to be outputting 17 volts. So the things that this powers run the engine and operate the vehicle. And then same thing down here. No matter what the battery's doing, our fans, our water pump, all that stuff is always getting the proper voltage and it never changes. So you'll have extremely consistent cooling for the engine, which is these two. The wideband is going to be steady. The trans brake is always going to open and shut and release exactly the same because it's always going to have the same voltage. Not that the running lights matter. This stuff is big, so the coils are going to have 17 volts all the time. So these coils are going to put out a shit ton of power. We'll get into that later. But the reason we did this, the higher voltage, is for higher power. Power goes up with voltage to the square. So when you start raising your voltage, you get a lot more power. The injectors, by giving these a constant voltage, they open and shut quickly and they're very predictable, but they always do the same thing. So, for example, tuning injector dead time is just not even a thing. And weather-related changes affecting how the injectors open will be minimized. It won't be stopped because temperature is a thing, but having a high voltage helps to minimize that. The computer will always have the same voltage, and the fuel pump, this high voltage going to the fuel pump, is actually going to make the fuel pump live an easier life. It's going to draw less amps, run a little bit faster, and it's always going to make the same fuel pressure. It won't have voltage fluctuating, which is critical. Worst thing that could possibly happen is you get on the big end of the track, and right before you're about to cross the finish line and let off, your battery voltage is dropping, your fuel pressure comes down, and you start to lean the engine out. That would be terrible. So, as you can see, yes, there's a weight penalty, and Lord knows the engineering to pull all this off, but it's going to put a very reliable and consistent electrical system in the vehicle. And I guess the last thing I'll touch on, yes, this is going to add weight. I don't know the exact numbers yet, although I am working on it. But remember, we had to put something in the car anyway. Typically, you have a battery and you typically have an alternator. So you would have at least had to do those two things before. And I don't have to do an alternator, the brackets, the wires, the cable, the belt, all of that's gone. So that weight's gone. And then for the battery, if you were only going to run a battery anyway, there's trade-offs. Like if you put a battery that weighs 20 or 30 pounds in a drag car, you just don't have a lot of capacity, and it's not going to last a long time either. From what I've seen, they don't last that long. Whether you're talking about before they need charging or before they need to be replaced. So the great thing about this is likely going to last until I just decide to remove it and upgrade it. This thing is rated for 6,000 cycles. I will probably manage to get, my guess is I'll probably get 1,500 to 2,000 cycles because of how I use it. It's going to be starting an engine, which is going to pull that 2C rating. It's going to get hit with that sometimes, but this will probably last for years. And I mean years with good performance. Like this battery will start at 100% capacity. Maybe 5 years from now, it'll be at 90% capacity. But 280 amp hours is so much battery capacity that I haven't actually done the math yet, but it's possible that I could charge the car, go to the drag strip, and never charge the battery the entire time I'm there. Run, for 4 or 5 hours drag racing and never charge the battery. I don't know if that's true yet. We'll see. It's not a big deal to charge the battery, but for sure, not going to have battery issues. As long as we plug in once in a while and throw some power in this battery, we'll be able to run this thing all night and have extremely consistent power for everything. So I know that kind of went on for a while. We're going to wrap that up here. And when we come back next time, we'll get into more of the details of all the engineering that's going into this to spec all the power, because you kind of have to work backwards. These things are givens over here. We know we need this stuff, so then we have to spec this, and you just work backwards. So I'll show you guys that in the next one. So until next time, y'all take it easy.